So here is the practice test review for the molarity and precipitation reactions quest. It'll be on Monday. What volume of a 1 molar solution of sodium bicarbonate contains 0.350 grams of sodium bicarbonate? So the first thing we need to do is figure out how many moles of sodium bicarb we're talking about here. So the molar mass of sodium bicarbonate is 84. You add up the sodium, the hydrogen, the carbon, and the 3 oxygens. So to find the number of moles, we take the mass, 0.350 grams, we divide that by the molar mass of 84, and we get 0.00417 moles. So that's how many moles are in the 0.35 grams. And so if we have a 1.1 molar solution, that means it's 0.1 moles per 1 liter. And so if we have 0.00417 moles, the question is how many liters or milliliters. You could do 1,000 milliliters on the left and then get the answer be milliliters. When we do this out, we get 0.0417 liters, or it would be 41.7 milliliters. How many milliliters of stock sulfuric acid solution, which comes in 18 molar concentration, would you need to make 750 milliliters of a 0.250 molar solution? The dilution equation is the first molarity and the first volume are equal to the second molarity times the second volume. In this case, and this is a very typical type of problem, we're given the original molarity, what we want the final molarity to be, and how much of that we need. And the question is, how much of the concentrated stuff do you need to start with in order to get the right concentration when it's diluted to the amount that you want? So we're just plugging in the numbers we have, 18 molar times that starting volume that we're trying to find, and we're working at getting a 0.250 molar solution, and we want 750 milliliters. Again, the volume, in these problems, the volume doesn't really matter unless you're asked specifically, which you are in this case, milliliters. But if you were given liters and it just said what volume, your answer would come out in liters. If you're starting with milliliters, your answer comes out in milliliters when you're doing these types of problems. So just keep that in mind. If you're doing molarity, you always have to keep in mind that the 0.25 moles is 0.25 moles per liter. So if you're doing that kind of question, you need to make sure it's in liters or thousands of milliliters. So when we do this out, we end up with 10.4 milliliters of the stock solution would be required to dilute down to 750 milliliters at a concentration of 0.25. So in this problem, we're actually doing a little bit of backwards reverse engineering. We want to know, what is the molar mass of this compound? Well, the first thing we need to do to find the molar mass is to find the number of moles. And it says it's a 0.25 molar solution, and we have 625 milliliters of it. Well, if you have 625 milliliters of a 0.25 molar solution, that should contain 0.15625 moles of solution. So we've got 5.75 grams, and that is 0.15625 moles. So if we divide that, we would find that the answer is, the molar mass is 38.6 grams per mole. So this is a solution stoichiometry problem. First thing we need to do is check the balance on the equation. And we should see or note that we've got 3 nitrates on the left, 1 on the right, 3 hydroxides on the right, and 1 on the left. So to make that all work out, if we put the coefficient of 3 in front of the potassium hydroxide and the potassium nitrate, everything ends up balancing out. So the next step that we need here is to find the limiting reactant, because we're given both reactant solutions to start with. So if we have 0.2 moles and we have 50 milliliters, which would be 0.05 liters, that means that we have 0.01 moles of the aluminum nitrate, and we have 1 molar potassium hydroxide, and we're given 200 milliliters, which is 0.2 liters. We have 0.02 moles of potassium hydroxide. So we have more moles of potassium hydroxide, but according to the equation, we need 3 times as much potassium hydroxide as aluminum nitrate. And we don't have that. The ratio we have here is 2 to 1 instead of 3 to 1, which means that the potassium nitrate is going to be the limiting reactant in this problem. So if we have 0.02 moles of potassium nitrate, the ratio in the equation of potassium nitrate to aluminum hydroxide, which is the precipitate, is 3 to 1, or in the mole ratio we have 1 to 3, because we're trying to find the unknown, which has a coefficient of 1. So 0.02 times 1 over 3 gives us 0.00667 moles of aluminum hydroxide, and then we can multiply that by the molar mass, which is 78, and we see that we would get about half a gram, 0.520 grams of precipitate in this reaction. Why do these factors affect the solvation rate of solute, agitation, surface area, and temperature? They basically all come from the same thing. More collisions equals faster solvation. All right, so how do each of these do that? Well, the first thing is agitation mixes the solute and the solvent together. It gets the solute away from the surfaces of the underlying solute, which allows more collisions between the underlying solute, so that increases the number of collisions. Increasing the surface area increases the collisions because you're giving more opportunity for the solvent to get at the solute. Every time you split something in half, you create more surface area. You're creating more area for the solvent to get in there. That increases the collisions. And temperature, you're really talking about the energy of the particles, how fast they're moving. If they're moving faster, well, then they're going to have more collisions because they're just moving faster. So every collision leads to another collision or another. So they're more energetic, which means they're going to have more collisions, and that increases the rate of solvation. What is the difference between solvation for ionic and molecular compounds? Well, an ionic compound or an electrolyte compound, when you dissolve that in water, what happens is each individual ion of sodium gets surrounded by water molecules, and then the chloride ions get surrounded by water molecules. And the individual ions are actually separated from each other. The ionic bond is broken by the very polar bonds of the water molecules. So these things are dissociated into their separate components. In a molecular compound like a sugar, the sugar molecules, say sucrose or whatever it is, are separated from the other sugar molecules, but the individual bonds within that sugar molecule remain intact, which is why they don't conduct electricity. They are non-electrolytes. Why does the polarity of a solute affect solubility in water? Well, we touched on this in the last problem. In order for water molecules to sort of attack a solute, what happens is the very polar nature of the water molecules have very strong areas of positive charge around the hydrogens and very strong areas of negative charge around the oxygen. So when you have another polar molecule, which has a positive and a negative side, like an ion, well, the positive is very attracted to the oxygen end of the water molecule. The negative side of the other polar molecule is attracted to the hydrogen, and this is what allows the water molecules to kind of latch on and pull apart the solute. If there is no polarity, if it's just a nonpolar molecule like an oil or things like methane and things like that, the negative and positive poles of the water molecule don't really have any place to grab onto the solute, and so they are not able to pull apart either the individual particles or the molecules of that compound. So that's why things like oils don't dissolve in water, because they're nonpolar. The water molecules don't have any poles to grab onto. So here we're going to try to write the net ionic equation for the next few reactions, assuming there is a reaction, and you need to know your solubility rules for this. So the first thing to do here is to make sure the reaction is balanced. The only thing we need to balance the equation here is put a 2 in front of the lithium acetate, and then know that these 3 species are soluble. Carbonates a lot of the time are not, and certainly a cobalt carbonate is insoluble, so that's going to form a solid. So what we're looking at here is, what does the cobalt ion and the carbonate ion look like when they're aqueous? That will be what we show on the left of the net ionic equation. On the right hand side, we're just going to have the cobalt carbonate solid. That's the only product. These are spectator ions because they are soluble. All of the salts of alkali metals, including lithium, are soluble in water. So the reactants in this case are the cobalt ion, which is a +2, and the carbonate ion, which is it's a 3, it's a -2 charge. So it's a pretty simple net ionic equation. You've got the 2 ions, one's a +2, one's a -2. So when you put them together as the precipitate, it's just a 1-to-1 ratio. All right, so what would the products be here? Well, you have to work out the charges. Since nitrate is a -1 polyatomic ion, and there are 3 of them in this compound, that means that this iron is an iron 3, an iron with a +3 charge. Over here you've got potassium, which is a +1. You've got sulfur, which is a -2. So on the right hand side, the products will be potassium nitrate and iron sulfide. It's going to be iron 2s sulfur 3, because this is a -2, this is a +3. So you need 2 irons and 3 sulfurs to get the total charges to be 6 on both sides. And again, we've got a alkali metal salt, so this is going to be soluble. A lot of the sulfide compounds are insoluble. There are a few exceptions. Iron is not one of them. So this is going to be the solid, the insoluble precipitate. So our net ionic equation is iron, actually 2 iron, 3 plus 3 sulfur, 2 minus, and these are both aqueous, produces iron 2 sulfur 3 solid. Lead nitrate and lithium sulfate. So we're gonna have lithium nitrate. That will be aqueous. Again, it's an alkali metal salt. Also, nitrate salts are pretty much always soluble, which means we just have to look at the lead and the sulfate. And in this case, they're both 2 charge ions, +2 and -2, so they go in a 1-to-1 ratio. Some sulfate compounds are soluble, but one of the exceptions is the lead 2 ion, which is what we have here, so that's going to be a precipitate, which means that our net ionic equation is lead 2 aqueous plus sulfate minus 2 aqueous produces lead sulfate, solid. And the last reaction, we've got ammonium chloride and copper acetate, and we're going to need 2 ammonium chlorides because we're going to end up with ammonium acetate. Plus copper chloride, which is CuCl2. And we're going to have 2 of these, so that balances everything out. And in this case, all of the product species are soluble. So in that case, we say no reaction, because you've got aqueous ions floating around in each solution. When you mix the 2 solutions together, all of the ions are still just floating around, so nothing has changed from left to right, and therefore that's not a reaction. It's just a bunch of ions floating around. So there you have it. Make sure you know your polyatomic ions and your solubility rules. I gave you that chart in class. You can also look at the book, which has sort of a simplified version of what the general rules are. That might be easier to memorize, but you do need to know your ions too. So that's it. Good luck. We'll see you on Monday.